I see that.
Okay, cool. Great, yeah, keep them coming because, yeah, that's right.
Earlier you had mentioned PD is not part of BLF testing or tangent.
So in this case, it will not be a part of, yeah. So PD is usually performed at either power frequency because that's what the system actually sees. So VLF testing, I'll give you two examples. One will be your tan delta, but the other VLF test will actually be a VLF high pot. And the nice thing is you're familiar with high pots, DC high pots at this rate, but instead of direct current being applied, it's going to high pot, overstress it at this long period of time, like a long sine wave. And again, the idea being that it will be non-destructive. That is the viable alternative to high potting service age cable, which again is that's the one takeaway from this class. We'll be happy with that. Do not DC high pot service age cable. But VLF provides that alternative. So excellent question. All right, very good. Okay, and so we talked about the mathematical relationship here. Again, your tan delta test will be supplemented with your VLF, which provides the sine wave. So here are our test results, our loss angle, tan delta. And so this will, again, comparing the capacitive and reactive components. For new cable, it's very steady. Now the way these will work is you'll actually step up the voltage, right, at increments. First you'll do 2.5 and see how the capacitive and resistance interact. Then you'll set it to 5 kV, right? And again, you'll see how the capacitance and the resistance kind of interact. And eventually you'll hit your maximum value, which is dictated by beta MTS. But new cable, what do you notice about new cable?
It's strange.
Good to go. Yeah, pretty stable, very stable, right? And again, this value is almost zero, right? Almost zero in terms of that loss angle, right? And zero. Yeah, zero angle just means that if this is zero, then this I is exactly equivalent to your ICP. Right? But as this angle gets bigger, which we're seeing for aged cable, right? That angle will continually show that it's increasing, especially as you step up in terms of voltage. So we see that measurements are voltage dependent in old cable, whereas with new cable they are not. All right, and then I believe in that same NETA MTS table, we'll see our acceptable All right, there we go. So this is our cable, and we're familiar by now what XLPE stands for, our cross-linked polyethylene we talked about at length last week, as well as our EPR, ethylene, propylene, rubber. All right, so these two extruded dielectric cables, they're going to have different evaluation criteria, right? And so in this case, we're saying what is acceptable and what is not. Okay. So if it's less than 0.1, and we'll look back at this example chart, definitely less than 0.01. Okay, so then it's going to be acceptable. But what it does is it actually, you have to compare each of those voltage steps. Right? And so if we see a deviation greatly between here, if we see a large deviation, I'll actually pull up a report that we've done in my company during, I'll have a break pretty soon. I'll show you how we evaluate that one and make our determination. But this chart, yeah, this is the one we're going to follow to tell our customer exactly what like we told them when we just look at the dielectric absorption and say, good, dangerous, whatever. We're going to say acceptable, further study, or action required. Right? We know how the NETA MTS tables work, and if we can find the correct column that our numbers fall into, we'll be able to determine pass or fail. Right? And then write that up in a comprehensive manner to our customer. We're going to have the data to support that, right? And then that is exactly how we pay the bill. So, let's see how many more of these. Yeah, this would be, before we go to PD testing, we're going to take a break. At about 8:15, I'm also going to take the time to set up, find a real world tan delta test report from it. Cool. We'll see you then. And if anybody had any questions, feel free to come up as usual.